So Shouvik, please stop sharing. Now we have Aritra Ghosh, who will talk on contact and metric structures in black hole thermodynamics. Aritra, please share your screen.
Okay, so am I audible?
Yeah.
Okay, good. Let me try to share my screen.
So you have 12 minutes and then 3 minutes for question and answer. I will remind you after 9 minutes, okay?
Right, okay. So are you able to see my screen?
Yes.
Okay, so let me go to this full screen mode.
Full screen mode, yeah, you can go.
Yeah,
good.
So this is visible, right?
Yeah.
So, right. Okay.
Please
so
go.
So thank you, Prashant. So I would like to begin by thanking the organizers for this opportunity. And the title of my talk would be Contact and Metric Structures in Black Hole Thermodynamics. And it's based on work done with 𝗰𝗵𝗶𝗶𝗶. So the brief outline of my talk is as follows. I'll begin with some motivation. Then we'll do some brief recap of symplectic and contact geometry. And after having done that, we'll actually look at some geometrical aspects of thermodynamics and Hamiltonian description of thermodynamic transformations. And finally, I'll actually give maybe make a few remarks on metric structures and thermodynamics, and we'll exist by pointing out a few existing challenges. Okay, so all of us know that black holes are associated with the notions of entropy and temperature, which are given by these relations, at least in Einstein gravity. And the first law of black hole thermodynamics kind of looks like this for a Kerr-Newman-Radius black hole, where the last term, the P, this arises from a cosmological constant. So something that all of us are aware of is that thermodynamic variables such as P and V, or T or S, or maybe omega and J, with J is angular momentum, these things always appear together. So this is something we have seen way back from our high school days, that we have terms such as S, dt, and TdS. They always kind of stick together. So it kind of points towards a mechanics-like description of thermodynamics, things like associating the notion of a coordinate and a momenta, which are in a sense conjugate to each other. So the purpose of this talk will be to briefly explore these, the geometric mechanics framework of black hole thermodynamics. So let us begin by kind of recalling the notion of a symplectic manifold. So symplectic manifold is a smooth manifold of even dimensions on which you have a two form which is closed and non-degenerate. So if this is the case, then if you're given any smooth function, H, then you can always associate a vector field XH through this relation. You have a vector field XH, you contract it with, so this I is basically the contraction symbol. You contract it with this two form, it gives you one form, and that is the H. So this is, and because omega is like non-degenerate, so it is invertible, so this is an isomorphism. So there is a unique relationship between DH and XH. And XH is called the Hamiltonian vector field, and this is a volume preserving thing. So this is something in StatMech we know as Weyl theorem, and this turns out because if you take a lead derivative of omega with respect to XH, it gives you 0. So that's the Cartan formula. The second term vanishes because omega is closed. The first term vanishes because the d square is anyway 0. So there's a famous Darboux theorem which asserts that all symplectic manifolds have the same kind of local structure, and you can associate a local coordinates to any open patch, 𝗰𝗵𝗶𝗶, in which omega always looks like this. So this is always, so irrespective of what is the topology, it doesn't matter, locally it looks like this. And it's not difficult to verify that the XH Hamiltonian vector field kind of looks like this in the local coordinates. So that this condition is satisfied. And this actually gives us our familiar Hamilton's equations. And as a remark, the Poisson bracket is defined like this. For any two functions, f and g, it's just the contraction of the corresponding vector field with omega. So similarly, there is something called contact geometry. It's like an odd dimensional yet a little less symmetric counterpart of symplectic geometry. And a contact manifold is a pair where M is a smooth manifold, this time of odd dimensions, and eta is a one form which satisfies this condition. So this is like a volume form which is non-zero. But if you look from the Frobenius integrability sense, you'll find that this condition being non-zero means that the vector subbundle of the tangent bundle generated as kernel of eta is completely Frobenius non-integrable. So the hyperplane distribution is extremely twisted hyperplane. So there exists a globally defined vector field. So this is globally defined. It's called the Reeve vector field, which is defined through the following conditions. So the first one actually tells you that eta is in a sense it's dual to the one form, as in Xi is in a sense dual to the one form eta. In case of contact manifolds, you have an exact vector bundle isomorphism similar to the symplectic case, for which if you are given any function h, smooth function, so then you can associate a vector field xh. And there's a similar W theorem which asserts that eta will look like this in the local coordinates. S is one unpaired coordinate and Pi, Qi are like conjugate variables. And in these local variables, your Hamiltonian vector field looks like this. Your vector field xh looks like this, and it kind of looks like a Hamiltonian vector field. So we'll just end up calling it the contact Hamiltonian vector field. Okay. However, let's point out that there are two features which this contact Hamiltonian vector field has, the Hamiltonian vector field doesn't have. First of all, the contact Hamiltonian vector field is not volume preserved. If you take a divergence in the local coordinate, you find that this is in general non-zero. As long as H is independent of, as in H is dependent on S, which is the whole point. If you remove that unpaired coordinate, then you are actually not doing contact geometry at all. So the dependence on S is essential for things to be kind of non-trivial. And this vector field also doesn't conserve H, unlike the conservative Hamiltonian. So in conservative Hamiltonian mechanics, the Hamiltonian is conserved. But in this case, it's not conserved in general, unless H is zero. So of our interest, there will be a very special class of submanifolds, which are the submanifolds. These are like maximum isotropic submanifolds, which are submanifolds of maximum dimension such that the contact form eta is zero when restricted on the surface of the submanifold. So more technically, you can think of if F is the inclusion map, then the pullback of F star eta is zero. It's just like a configuration space or a Lagrangian submanifold of a symplectic manifold, where you don't have conjugate pairs of variables. The fact that eta is zero means that you cannot have conjugate coordinates. So now, if you recall the first law of thermodynamics, so first laws always have forms like this. Like you can have different work terms, but the first law of thermodynamics always looks like this. So if you compare this one with the local expression that eta always, so Darboux theorem guarantees you this, that locally you can always write the contact form like this, irrespective of whatever might be global properties. Locally you can write it like this. So if you make this comparison, you can actually think of associating a contact structure with a thermodynamic phase space, where the local coordinate corresponds to the thermodynamic variable. So you can think of at least locally thermodynamic phase spaces as contact manifolds, and then you can actually do certain things like there are generalized Poisson brackets called Jacobi brackets. You can define bracket kind of relations between thermodynamic coordinates. The interesting aspect is that at equilibrium, the first law should hold. So if it is zero, that means that eta is zero. And eta is zero, as we saw, is the definition of a maximum isotropic submanifold. That means equilibrium states, the states which satisfy the first law, they are all points on a Legendre submanifold. So even if the entire phase space, the ambient phase space is a contact manifold, but the equilibrium states don't have access to all the points, they lie on some kind of submanifold L. So we call it L. And contact Hamiltonian dynamics, it implies kind of evolution of variables, evolution of thermodynamic variables, because thermodynamic variables are now local coordinates. So therefore, Hamiltonian dynamics can actually describe thermodynamic transformation. However, H is not conserved, so an arbitrary XH is actually not tangent to the level surface H equals to zero, or levels as in a Legendre submanifold L. However, if L actually is a subset of the level surface H equals to zero, that is, if you choose carefully a contact Hamiltonian which vanishes on the Legendre submanifold, the space of equilibrium state, it may not be vanishing everywhere, but on that space of equilibrium states at least it vanishes, then the contact vector field, if at initial point we choose on that surface, on the L surface, it's actually going to stay on that surface throughout its evolution. So you can think of all the points lying on the integral curves of that vector field, provided one of the initial points is, as in one initial point is an equilibrium state, all the subsequent points are equilibrium states. So you can think of a Hamiltonian description of thermodynamic transformations of a system. So for example, I'll take a very simple example, is that of the BTZ black hole whose mass is 4 square over pi, and thermodynamic volume is simply just del m del p. If you choose the following form of the contact Hamiltonian, a simple computation of the vector field in local coordinates reveals that T dot is zero. So this can point towards an isothermal transformation of the system. Now, since for the BTC black hole, you have this relation between B and S, if you substitute this relation into the expression for H, you get something like this. And this is zero on the space of equilibrium state of the system because of what's called the Smart relation. So it's like an Euler relation for black holes. It's the three-dimensional Smart relation where, so it's like, although the Hamiltonian is non-zero off shell, it's going to be zero on shell, something like that. So that means the flow, provided an initial point you choose, which is an equilibrium state of the black hole, all the subsequent points are equilibrium state, and it's an isothermal transformation. And it's actually simple to check that the P and V evolution equations, the Hamilton's equations for P and V, they satisfy all the thermodynamic quantities. So similarly, you can choose this kind of choice, which can generate isobaric transformations. You can, if you're smart enough, you can choose anything for any system you take, you can find a Hamiltonian.
Sorry, Aritra, you have 3 + 3 minutes.
Okay, so 10 minutes is over, right?
Yeah.
Okay, thank you. Thank you. So, okay. So another aspect is that if H is not vanishing on L, so the previous case was that when H would, the chosen Hamiltonian would vanish on the Legendre submanifold. If it doesn't vanish on L, then the resulting flow need not be tangent to L. So even if you take an initial point, which is an equilibrium state, your integral curves may not actually stay on that submanifold. So the subsequent points may not be equilibrium states of the initial system that you started out with. However, such a transformation, such a Hamiltonian flow can be taken to generate a family of related thermodynamic systems. For example, for a Schwarzschild ADS, if you choose this kind of Hamiltonian, this is something works with a little bit of guesswork and a little bit of constant later. So it turns out that T, under the vector field, T and V, they do not evolve, whereas P evolves in the following form. Here, the first two terms on the right-hand side correspond to the equation of state of the Schwarzschild ADS black hole. Whereas the third term, this is the term which depends on tau. Tau is like an affine parameter. You may not think of that as time, some parameter which parameterizes the Hamiltonian flow. So when tau is 0, you're on the initial point, you're on an equilibrium state of a Schwarzschild black hole. Now, as you increase your tau, you happen to get equations of state of charged black holes with charge values q squared tau. So you can generate an infinite number of charged black holes via a Hamiltonian transformation. So this is one different aspect. So okay, so I'll put a remark or two about thermodynamic metric. So this is called the Ruppiner metric, which is defined as the negative Hessian of the entropy. And this actually agrees with the Fisher information matrix, which is defined in terms of the density matrix of a system. That is much more general, of course. The thermodynamic limit may not exist. This is defined in the thermodynamic limit. Now, this is very intuitive, which can be seen by writing. You can take your Boltzmann entropy omega, and you can write omega as exponential s. You can invert the formula. And if you expand entropy about the equilibrium to the second order, then you can argue that the probability of finding the system between Zi and Zi plus Dzi is actually proportional to exponential of that length, negative length. So it's like more the distance between two states, the less probable is the fluctuation between them. So that's why this Ruppiner's metric is kind of intuitive, and it has been empirically demonstrated that the curvature scalar of the Ruppiner metric, the Ricci scalar, possibly carries some useful information about post-strained microscopic interactions. So these are still in some speculation stages. So the final thing which I would like to point out is that such metric structures, Hessian metric structures, can actually arise from the contact structure of the phase space, thermodynamic phase space. For example, Sasaki, he actually introduced the concept of a contact metric manifold. So these things actually carry his name. They're called Sasakian manifolds. So where you have a metric which is compatible with the contact form, and so that there is a compatibility condition to be satisfied. So it turned out that if you project this kind of metric, if you choose your thermodynamic potential slightly carefully, if you project this metric on the Legendre submanifold on a space of equilibrium states, you get the Hessian structure back. So that is a wonderful thing, that the geometrical features of the thermodynamic phase space actually incorporates everything. And Hessian geometry seem to offer insights into the phase structure and microscopic interactions. So you can think of that as a macroscopic probe for black holes, in which you're not able to directly compute microscopic things possibly. So as a simple illustration, I'll just show a comparison of the thermodynamic curvature, the Ricci scalars, these are the Ricci scalars, versus the fugacity of an ideal Bose gas and the large black hole branch of a spot-shelled black hole in ADS 510. So there was a proposal a few years back. Dolan made this proposal that if you take a dynamical cosmological constant, on the boundary side, it would mean that you're varying the number of colors, you're varying the number of degrees of freedom in the larger limit. So then a Schwarzschild black hole in ADS 510S5, in the fugacity goes to one limit, which is the Bose condensation limit, appears to have a similar condensation effect. So we wanted to just check whether, because of certain claims that the thermodynamic curvature could capture microscopic interactions, we wanted to check if the curvature scalar shows some similar behavior, and we actually indeed find something very nice. It looks like this. Okay, so okay, so I'll just end with some existing challenges. So first of all, the first thing is that some kinematic properties, like for example, we did some Hamiltonian flows, but the fact that because these flows are not volume preserving, you can have focusing effects, you can have sources and sinks. So certain properties such as existence of sources and sinks, their significance, and things like shear and rotation characteristics, the ones that you look for when you're writing right-order equations and all for geodesic flows. So things like that have, I think, is worth investigating. And thermodynamic Hessian metrics, although they're nice, they're related to fluctuations, they have a serious drawback of not being invariant under Legendre transformation. So they are sensitive to the ensemble that you choose. It depends on what is the free energy that you choose. So thorough comparison and classification in that regard is something which is yet of a challenge, because a lot of things are empirical. You don't have exact results for most of the time. So, okay. So all the thermodynamic Hessian metrics define distance between states, equilibrium states. But we saw that things like a Schwarzschild black hole can be mapped into a charged black hole via Hamiltonian flow. So kind of things like distance between states, distance between different thermodynamic systems related by Hamiltonian flows, things like that are still open. So I think I'll stop here. Maybe I'll take questions. So thank you.
Okay, thank you, Aritra. We are running out of time, but if there are any one or two quick questions, then we can take. Okay. Okay, if there are maybe if there are questions, we can take it in the discussion session. Okay, thanks, Aritra. Thank you very much for the nice talk. You can now stop sharing.
I'll unshare my screen. Yeah.
So